Hi, I'm Jonathan Aldrich. Let's talk about implementing type checkers. In order to implement type checkers, we need to write functions that traverse the abstract syntax tree in a similar way to the interpreter that we already discussed. We could pass around a type context explicitly so that our type checker can look up the types of variables when it needs them. But it's more common to use a symbol table to do this. A symbol table maps a pair of the scope that we are in and the name we want to look up to the type of that name in that scope. There might be other information attached with it as well, but we'll focus on typing here because we want to type check as our goal. We pass the current scope to the type checking procedure so we always know where to look up variables. We're also going to assume an error function that reports an error to the user. The error function will return a special error type that acts as a stand-in for a type, but we're going to use it to avoid cascading type errors. So if you have a type error in one place, then some things that are dependent on it will not also produce type errors. Let's look at the implementation technique in more detail. Here we have a function for type checking expressions. It takes the scope that we're currently in and the AST of the expression that we want to type check. It will return a type for that expression. We do a case analysis on the AST. This is similar to figuring out which of the typing rules applies. In this case, we figure out which typing rule applies just by the form of the expression. If the expression is an integer literal, then we'll return integer as our type. If it's a real literal, we'll return real. These correspond to the tintlit and treallit rules. If we have a variable, then we need to look it up in the typing context. In this case, we're going to use a global symbol table to do that. So we declare a variable for the type, and we call a getType procedure on the symbol table, passing in the variable that we're looking up, the scope that we're looking it up in, and the AST. The AST is not needed for the lookup itself, but if X is not found, then getType will call an error routine. And the error routine needs to be passed, first of all, the variable is not declared, right? Because we found a variable that's not in scope. But we also need to pass the location of the error, which in this case is the place it's using X where it's not declared. And so passing in the AST A is basically giving some information to the symbol table so it can report error messages better. The symbol table, if X is not found, will actually add X to the scope with the error type, which will avoid cascading error messages. So that if X is used again, we won't generate another error. We figure that the user will probably fix the first error by declaring X, and we'll never even get the later errors. Assuming that the type was returned correctly, though, we'll return it. Actually, even if it's incorrect, getType will return the error type, and so that'll work out just fine. A similar scheme is used for expressions like float. So if we have a float expression, we type check the sub-expression. So this is a recursive call. And that recursive call corresponds to the premise of the typing rule for float. So premise turns into a recursive call of the type checking routine. In this case, we pass in the same scope and the sub-expression A1. If we don't get an integer type back, then we already have a real number, and so we'll issue an error. We'll return type regardless for the type of the float. Now, of course, the type from type checking the sub-expression could have been an error if there was an error there. In that case, we also just assume we have a float and we go on. Truncate is similar to float, and then binop is a little bit more interesting. As we saw, the typing rule for binop has two premises that type check sub-expressions, and so those turn into recursive calls again for the sub-expressions A1 and A2, again in the same scope. If the types are the same, then we'll return one of those types. It doesn't matter which one since they're equal, and we will have succeeded in type checking this binary operation. Otherwise, if one of those is an error type, we'll return the other one, assuming that when the user fixes the error, that will be the type of the expression. Otherwise, maybe the two sub-expressions did type check, but at different types, and so we'll raise a mismatch type error and return the error type. How do we type check statements? Well, it's similar to expressions, but now we're going to be changing the symbol table and manipulating the scope. So if we come to a declaration of a variable x, then we'll add x at type integer to the scope, and again we'll return the current declaration statement A as a place to report the error message. If x happens to be already present in the scope and it isn't of the error type, then this add message will set the type to error type, and it will call an error that says the variable is already declared in the scope. It will set the type to error type only if the two different declarations differ, but we'll report an error, of course, either way. After adding x to the symbol table, that's essentially like adding x to the context, right, in the typing rules, then we will type check the statement. Again, using the same scope. In our implementation, we're just adding variables to the scope one by one as we go. We don't create a new scope every time a variable is declared. We would do that if we go inside an if statement or something, which is something I'm not showing in this particular type checker. But we'll go on and check the statements S, which are the statements following this declaration in the same scope. So that's a recursive call, which again was a premise from our rule for int declarations. A real decl is very similar. Assignment is a little bit more interesting. Now we're going to type check the expression on the right. That's a recursive call. I guess it's a call to the type check expression procedure, which is the one we saw before. We look up in the symbol table what the current type of x is, and then we check, is that the same as the expression on the right-hand side? So if the types are different and neither one is an error type, then we'll report a mismatched type error. Otherwise, we go on and type check the rest of the program. Read and write are fairly similar in how they work. Read operates by getting the type of x to make sure it actually exists. We'll report an error if it doesn't. Otherwise, we just continue on reporting the statements that come after the read. Write will type check the expression, just make sure it has some valid type. We can print it no matter what type it has, and then we'll go and type check the rest of the program. And finally, if we get null, which is our way of representing the empty program, we just return because there's nothing to do to type check it. Let's check our understanding.